later on, the component which caused the failure was identified as non-critical and just destroyed the whole rocket. Knowing that, why not certify everything on level A? Because level A needs a lot of attention. The DO 78B just identifies them as objectives. Objectives are documents and attributes to documents, like the document has to be very thick or very thin or whatever. No, they're really quite clear definitions how it should look like. And if you go up from no effect to catastrophic, the objectives raise. So if it's just minor, you have 28 objectives, which are quite easy to cover. But if it's a catastrophic one, you have to invest a lot of effort to find that. In addition to that, there is so-called independence, where I will come to later on. And just to look forward, independence means much more effort. This is an example for an objective sheet, where how it is located in the DO 178B. Some objectives in here. High-level requirements are accurate and consistent. That's quite clear that for every level that has to be mandatory or independent. Independent means that someone else has to look for it. But high-level requirements are verifiable. Maybe for level D this is not important. Also the output of this document has to be verified, depending on the category. As you can see here, there is no level E, because E doesn't have any effect and doesn't have any impact, so it's not mentioned. Now let's have a look at the process in itself, because you have seen a lot of documents, how they interact. First of it, if you just have the idea, you want to develop a plane, especially software for a plane, you're writing a so-called PSAC. That's a plan for software aspect of certification. It's a document where you just describe what you're intending to do, and you send this document to the FAA and to the EASA, which will now have a look at you and on your project. It's just the entry of the project. Then you start a so-called software configuration index. This is more or less a list of artifacts you're intending to produce or producing. Documents, source code, test cases, whatever is part of your development will be listed in here. You start that, it's not finished. It will be filled during the project. The next thing what you do, and every good software developer will do that, you're making plans. A plan for how do you intend the development should go on, how you intend the verification should go on. These are really schedules. Really, on May 1st, I will start coding. On May 2nd, it will be finished. And on May 3rd, I will detect that this is not true. But especially in here, it's not one plan, it are 4 plans. For development, for verification, for configuration management, like you want to set up the user version, and for quality assurance. Quality assurance is a very important thing in here, and I can say that the quality officer is the one who, if he comes to your office, you will have a clean desk or will be questioned. Then, of course, every good development has standards. You have seen coding standards where you just say, okay, if I'm coding in C, I have to have a nice, not every function shall not contain more than 10 lines or not more than 80 characters per line or whatever. Every company and every team has some standards. Also some design standards. We're just describing how you design. That you're doing a paper, that you have some chapters, whatever. And some requirement standards. This means how you write requirements, how you find the requirements. For the DO 178B, it's just important that they are here. What is in it? I hope this is something smart in it. Having that, you're studying the so-called Software Lifecycle Environment Configuration Index. It's a fine thing. It's more or less, as index indicates, a list, and the list contains just the tools you are using. it contains the operating system you're just developing to the compiler you're using. The important thing is that everything is listed, because it could be that one part which is in it is critical for the development, like your compiler. If your compiler does nonsense with your source code, then it's also, it has to be looked for it. So it has to be evaluated, and there are very expensive certified compilers if you really have to rely on what's coming out. Anyhow, you have to just list it with the version number you're using so that it can be reproduced. Okay, so that's my environment. Of course, I have my system requirements which just say the plane shall fly. And from that system requirements, I can start developing so-called high-level requirements. It's called software requirement data. It's a high-level view about your software. The software architecture is in it, and algorithms are in it, and it gives you an overview how the software is structured and what components are in it. Having that requirements, you immediately start doing test cases. If you're doing the test cases, if you have a requirement how your software should look like and what function should be in it, you're writing immediately in that case a test for it. Yeah. After having the high-level requirements, you continue developing the low-level requirements. It's called software design description, which contains a complete and accurate description of your software. Just see here, you haven't written a line of code till now. The low-level description should be good enough to completely describe your source code. It could be seen as a very good documentation. After having that, you can start coding, and you will develop your source code step by step. Of course, this is not one step after another process. You have to start things. So at the time where you development system requirements, the high-level requirements, you can immediately start developing low-level requirements, and you can immediately start source code. But you cannot finalize the low-level requirements before having finalized the high-level requirements. So it's just, that's the reason why it's a little bit stacked in here. And it's quite clear that if you haven't finalized your requirements, you cannot finalize your source code. Otherwise, that would be a failure in the sense of the 178B. Your source code and your verification courses will be tested against each other, and the result, hopefully yes it runs, will be collected in the so-called software verification results. It's just a list what the outcome of your test cases will be. Sometimes it's an important test case that a function shall fail. That's also a good thing. In the meantime, where you're developing, records will appear like problem reports. You're just collecting your problems, like the source code doesn't behave like specified and this kind of stuff. They have to just be collected. The same as the quality assurance, that the quality officer regularly reports, yes, he have had a look at your table and it was clean. And also configuration management records, like a snapshot was taken at this time with that tag. Having all that and having a good tested software, you can start with the SAS, with the software accomplishment summary, which is the document the FAA and the SAA is interested, which just says, I've done everything, here are the results, that's my process, here are the documents. And with that, you will get a wonderful ribbon, and the FAA will say, yeah, that's good software, and I trust you. So now I want to have a closer look to this requirement process, because I think this is the one which may be reusable for other development on a non-critical area. And everything starts with an idea that you want to build a plane, and system requirements like the plane shall fly, the plane shall carry people, and so on. And of course your system design standards. And every requirement from the system level has just a number, 1, 2, 3, and so on. So if you're starting now a high-level requirement, you just take the system requirement, have a look how you would implement that. You would make functions out of it, you will make algorithms, and so on. So every high-level requirement, every system requirement will get at least one high-level requirement. And during that time, also your software architecture is built up. And that has also some requirements, will be stated in here. It's also allowed to add requirements which are not related to the software architecture or to the system, because of maintainability or things like that, or if you want to upgrade your software, that is not within the system requirements. But every requirement where it doesn't have a parent above has to be clearly stated, and it has to be explained. What is not allowed is that the system requirement doesn't have a high-level requirement, because that's the first test, and if it doesn't have one, then it's not needed, or you just forgot it. So if you're completely with that area, you can start with the next layer. It's following the same rules. For every high-level requirement, you need at least one low-level requirement. Of course, it's allowed that one low-level requirement satisfies two high-level requirements. No problem with that. So, and again, if you have something which cannot be related to a high-level requirement, it's called derived, by the way, you have to explain it. Sometimes it's because of your software design standard. It says we have to have functions not longer than 20 lines. And of course, here again, no high-level requirement with a low-level requirement has to be satisfied. And having now so many requirements, you can start coding. And of course, the description of the low level is so good that you can directly write your code out of it. The same in here. And of course, again here, you cannot have low level requirements without code. And, much more important, you cannot have code without a requirement. So you have to relate it to someone. So that gives us a very good interlink that you do not have any code without a requirement, and you do not have a requirement without any code. So everything what is in your software now is specified. Just a small example, because high-level, low-level system, maybe it's a little bit confusing. Just imagine an automated beer brewing device where everyone wants to have at home. One of the system requirements would be that this device shall signal that the beer is ready, because if you're thirsty, then you're interested in that. So if I'm developing now my high-level requirement, I just state that there is a function called beer ready, and that shall detect if the brewing is finished. And, of course, I just interlink that with my high-level requirement. Because if I cannot explain why I'm getting this idea from, then it is certainly not a good requirement. And then going on the low-level requirement side, I can specify that the brew ready function shall return true, and it shall have the following algorithm. Algorithm, state charts, pictures also can be formulated as requirements. There is a long list, and it would take an hour what a good requirement is. But to summarize it, it must be feasible, it must be realistic, so you can reach it, and it must be testable. And like a bad requirement is, the plane shall hold attitude. Yeah, how you test that? Yeah, you can fly beneath, but it's not a good requirement. To finalize that, also other high-level, or in this case a system requirement, can be located to a high-level requirement. For example, this is a typical safety requirement that you shall not burn the beer, but it has the same high-level requirement, like there shall be a detect function which detects that the brewing is ready. Having that, you get a wonderful traceability matrix, and you can have every requirement. You can do that for every requirement. This is just a few from system level to code, but you can have just a list also for low-level requirement going up to the system level. And in our example, S23 having two high-level requirements, H14 and H22, having several low-level requirements.